interacting ecosystems.
Okay.
Floor is yours. We see your slides.
Yeah. Can you see my slide?
Yep.
Okay. So first of all, I would like to thank the organizer for this invitation. It's a pleasure for me to talk today at this great conference. And so today I'm going to present one of my current projects focused on new perspective on the emergence of multiple equilibria in large, highly interactive ecosystem, which is essentially based on these two works. The first one has been posted on Archive in September, and the other one is an ongoing work carried out in collaboration with Giulio Viroli during my second and last postdoc at ENS. So the field of theoretical ecology has gathered momentum in recent years, reached by an explosion of experimental results and increasingly sophisticated techniques. However, there are still a lot of open questions in ecology that range on how does the diversity affect the evolution of the other species? What about cooperative patterns? Are they ordered? Are they disordered? Is it possible to detect a multiple equilibrium regime or even more complex chaotic dynamics? So all these challenging questions have attracted a lot of interest in the last decades, but the true novelty compared to the past is that theoretical ecologists and physicists as well are no longer focusing on a small number of species, but on many, many species interactive in myriad ways in very complex settings. And so in this particular regime, we can take advantage of tools from statistical mechanics and statistical mechanics of disorder system to provide an effective mean-field description and point out emergent mechanisms and collective behaviors in terms of phase transition. So here, for the sake of shortness, I just reported a few works that opened the route to this new direction, starting with Solé, Alonso, and McCain in 2002, going on with Kessel and Streb in 2015, and Guy Boonin in 2017. And I also want to point out this work by one of the organizers, and Rémi Monasson, who essentially consider a reformulation of the MacArthur model in high dimension. And we reconsider with Silvio Franz this model in high dimension to rephrase this model as a constraint satisfaction problem and to show that constraint satisfiability can provide another complementary mechanism for explaining criticality and the appearance of marginally stable phase in large ecosystems. So today I'm going to present another problem, another canonical model in disorder ecosystem, that is the Randall-Lofgauter model, that has been recently shown, essentially in 2018, to be a good platform, a good reference model for capturing many different features for various communities models, essentially by tuning 4 control parameters. So the starting point in the Lofgauter model is the dynamical equation for the relative species abundances, Ni, relative in the sense they have been normalized to the total number of individuals in the species pool, where the dynamical equation takes this form, and I is an index that runs over the total number of species in the species pool. So we have a first self-regulation terms that is written as a gradient of a one species potential. And so it's a self-regulation, is a forcing term in the sense that if one species I experiences overcrowding in the immediate environment, it will be pushed back to its own value of the carrying capacity Ki. Then we have an interaction part that depends on this matrix alpha j. And by tuning this alpha j, we can essentially pass from a mutualistic regime to a highly competitive regime. And then on top of that, we want to add another source of stochasticity in the model, because we are aware of the fact that when we deal with invasion and migration, a stochastic effect can be paramount. So we had this noise, eta, which is modeled as a Gaussian noise with zero mean and covariance given by this expression. So it's proportional to the abundances Ni and to an amplitude T, which is essentially inversely proportional to the total number of individuals in the species pool. So the larger the population, the larger the abundances, the smaller the demographic noise. And then we also consider an immigration parameter lambda that at the first level analysis, we assume to be species independent. So it does not depend on the index I. So to get a well-established theoretical framework, an exactly solvable theoretical framework, we use some assumptions. So we start from a well-mixed community, no space dependence. we treat this noise with a etoformalism that allow us to have a conservative density. This means that if one species starts with an abundance is close to zero, it will remain there even if we inject a small amount of noise into the system. And then to tackle the staggering complexity of the ecosystem, we model this alpha ij as random variable extracted from a distribution without long tails. And the Gaussian distribution is perfectly fine, parameterized by the first two moments, so a rescaled mean mu and a rescaled variance sigma. And in this last hypothesis, so for this last hypothesis, we are essentially following Robert May, who was a pioneer in this field, who first studied stability and complexity in large ecosystems by random matrix theory techniques. So the first scenario that we can have is for symmetric interaction. So when alpha ij is equal to alpha ji. And so in this particular case, the dynamical equation that I showed before emits a quasi-stationary invariant probability distribution, which is associated to an energy function h, which can be written as the first part, the quadratic part that depends on the species abundances. So quadratically on the species abundances, an interaction part, and then we have two supplementary terms. So these supplementary terms exactly come out when we do the mapping between the dynamical equation and the static formalism by passing through a Fokker-Planck framework, a Fokker-Planck derivation. And so we have a first demographic term, which is proportional to this parameter T, that in physical jargon will correspond to a physical temperature. And then we have another term that allows us to model the immigration parameter lambda. And so to properly model this immigration, what we do is essentially to consider the log of a theta psi function. So the EV side function. So the EV side function means that when an I, so the abundance is greater than lambda, the EV side is 1, and so the log of 1 does not matter. Whereas when an I is smaller than lambda, this EV side function is 0, and so the log of 0 is minus infinity, that with a negative sign provide a reflective, reflecting wall, a repulsive boundary. So particle species bounce, and essentially they will be reflected. So this model was originally studied by Bunin in 2017, and then reproposed a year later by Biroli, Bunin, and Camarota, without considering the demographic noise and immigration parameter. So essentially they reproduce the phase diagram, they perform a thermodynamic analysis at 0 temperature, where they obtain the phase diagram in 2 dimensions for the heterogeneity parameter sigma as a function of the mean interaction mu. So I don't want to touch up on this phase, which is somehow unphysical and depends on a pathology of the model. So we should modify the Loft-Cabothard equation, but I want to focus on these 2 main phases. So when the heterogeneity are weak, when the interaction are weak or highly homogeneous, the system is in a single equilibrium phase. Then we can pretend to increase this parameter sigma, and what happens? So when we increase sigma, the system essentially crosses this red line, which is an instability line for the single equilibrium phases, corresponding to a sigma critical 1 over square root of 2, and so the system enters a multiply equilibria regime. So I want first to point out that this distinction between single equilibria and multiple equilibria regime turns out to be particularly timely nowadays, also in light of recent results in microbial community, as was pointed out by Jeff Gore during the first conference. And indeed, this heterogeneity parameter can be somehow considered the analogous of the variability of the influx of nutrients in your microbial community. And then I want to focus on this phase, on this multiply equilibria phase. As I said, the authors analyzed this model at 0 temperature, but now we want to understand what are the properties of this equilibria. And so in particular, what are the stability properties of this multiply equilibria regime, and how many equilibria are there? Are they exponential into the system size? Are they sub-exponential? So to answer this question, we consider the role of the demographic noise to study into more in detail the role of an intrinsic stochasticity. And we want also to understand what are the properties that derive from this demographic noise, and what is the suitable interplay between an intrinsic stochasticity and the immigration parameter lambda. So to do this, the main strategy that we use is to perform a thermodynamic analysis by using the replica method, which is a well-established, the well-known techniques in disorder system. So according to these techniques, we can compute the disordered free energy as essentially in terms of a replicated partition function, where n is the replica index. And so we have to compute this disordered average, disorder over these random variables, alpha ij. And so according to this definition, we need to introduce two order parameters that are the overlap, that essentially accounts for the degree of similarity between two replicas of the same system, A and B, and HA, which in physical terms would correspond to a sort of average magnetization, and here is the average abundances of the species for the system, for the replica A. So according to this definition, we can rewrite the free energy in this way, so as an integral over these new order parameters, so the overlap matrix and H. And since we are interested in the thermodynamic limit, so when the number of species S tend to infinity, we can take advantage of a saddle point approximation and obtain the stationary equation for QD, Q0, and H. So essentially, we can perform different handsets for these within this replica approach. And the simplest one is the replica symmetric handsets, meaning that this matrix QAB is just parameterized by two values. So QD on the diagonal and Q0 on the off diagonal. And this answer is perfectly fine in the high temperature phase, where essentially the landscape is purely convex and is just described by one single equilibrium. But when we start decreasing the temperature, the replica symmetric answer is no longer valid, and so it's not able to capture the increasing, the emerging complexity of the landscape. So in this particular case, we can resort to a more involved ansatz, which is a 1RSV ansatz, meaning that the original matrix is now divided in n over m blocks. Each of these m blocks contains m replicas. And so if I rephrase this metric structure in terms of the landscape, what do I get? So in terms of the landscape, I get now a two-level structure, which is described by two different off-diagonal overlap parameters. So Q0, which is the size of the largest basin, and Q1, which is the size of the innermost and deepest basin. So given these mathematical details, given these premises, we can essentially reproduce the phase diagram of the Loft-Volterra model with finite demographic noise and finite but small immigration. And so we can pretend to add another dimension to this phase diagram, which corresponds, as I said, to a sort of physical temperature. And so what we got is this two-dimensional phase diagram, because we discovered that there is essentially no sensitive dependence on the average interaction mu. And so we can reproduce just a two-dimensional phase diagram for the amplitude of the demographic noise T as a function of the heterogeneity parameter sigma. And so when the noise is sufficiently high, essentially to hide sufficiently high that random interaction do not play any role, the system is in a single equilibrium phase, and so the landscape is purely convex. Then upon decreasing the demographic noise or increasing the heterogeneity parameter, the system enters a multiple equilibria phase that I'm going to explain to more detail in a while. And going deeper and deeper in temperature, the system will cross this other line, this instability line in orange, where essentially the system enters a Gardner, an amorphous space. So to obtain this phase diagram, what we did was to look at the harmonic fluctuation of the free energy at finite temperature up to zero temperature. And so I mean that we have to compute the stability matrix, the matrix of the second derivative of the free energy with respect to this overlap parameter QAB, which embeds a first diagonal term and an off-diagonal part that can be rewritten as a 4-point connected correlation function. And so this matrix has to be properly diagonalized on a suitable subspace, and we have to look at the leading and smallest eigenvalue of this matrix that is called replicon in jargon. And so when this leading eigenvalue touches at zero, essentially it provides a criterion, a stability criterion for each of these phases. So this expression for the replicon eigenvalue is valid in this phase. And so when this expression is exactly zero, we get this line in blue, but it can be in a straightforward way generalized to attain this other line in orange, which provides the instability criterion for the multiple equilibria phase. So to recap this first part, I want to say that this phase diagram has been obtained in particular in 2 dimensions because we notice that there is no sensitive dependence of the interaction parameter. Now I want to explain more in detail these 2 intermediate phases where multiple equilibria phase emerge. And so in this particular phase, we perform a complexity computation or configurational entropy computation by following a technique proposed by Remy Bonassoni in spin glass literature, which essentially consists in computing the average of the log of the number of equilibria at a given free energy density. And so at a high temperature, we discovered that this complexity is strictly positive. That means that the number of equilibria is exponential into the system size. So it's exponential into the number of species S. And so this outcome is quite remarkable. In particular, if you think about stability, landscape, and ecological resilience concepts that have been proposed over the years to explain alternate stable states, stable equilibria, and multi-stability in a real ecosystem. Now I want to point out that there is another interesting features that emerge from this phase diagram, that is that at a very low demographic noise, a marginally stable amorphous space emerge where each of these equilibria splits, shatters into many subbasins according to a hierarchical structure, in close analogy with what happens in spin glasses and glassy systems. And so now we can wonder, why are we so interested in this Gardner phase, and what are the consequences also for the dynamics of this Gardner phase? So now I want to open a brief parenthesis to better explain why this Gardner phase is so important. So if we consider, for instance, a system of particles in high dimension, and we tune our control parameter, that can be the temperature or the density, we can have different phases. And so at high temperature or low density, we have just a liquid phase. So the phase space is purely ergodic, and the dynamic at long time is purely diffusive. Then upon increasing the density, the system can undergo a dynamical or clustering transition, meaning that this phase space splits, shatters into many basins, and the size of each of these basins, delta, correspond to the amplitude of vibration inside each cage, where the particles are essentially stuck or confined. And going deeper and deeper in temperature or increasing the density, the system can have another transition that has been recently discovered in glasses, in structural glasses in 2014, that is called a Gardner, in honor of Elizabeth Gardner, according to which each of these basins splits into many subbasins according to a hierarchical structure. And so if you look, for instance, at the distribution of particles, you have that to each of these particles correspond a precise network, a precise force network structure given by the particle in red. So given this landscape, so given these different phases that we have, and we can predict thermodynamically, what we can say, what are the predictions that we can get for the dynamics? So to answer this question, we also perform a dynamical analysis by using a dynamical mean field theory approach. And in particular, we look at the dynamical correlation function as a function of t and t prime. So we have to compute this average over all sources of randomness in the system, that are the sampling set, the interaction, the initial condition, and also the demographic noise. And so in the single equilibrium regime, this dynamical correlation function does not depend separately on 2 times t and t prime, but just on a single time scale, t minus t prime. So this essentially means that the dynamics is time translational invariant. And so as you can see from the correlation function at different t primes, all curves collapses to the same value, which is Q0, so the theoretically predicted value in the replica approach. And what happens in the multiple equilibria phase? Well, in the multiple equilibria phase, the system never settles down in any of these equilibria, but starts to explore the basin of attraction of the most numerous and marginally stable equilibria, essentially displaying engaging dynamics exactly as it happens in mean-field spin glasses. And so the two dashed lines in black and orange correspond respectively to the two parameters, so to the two overlaps Q0 and Q1 that I show in the two-level landscape structure at the intermediate temperature. So here I want also to compare the thermodynamic quantity that we can get in a replica symmetric ansatz. That means, so the average abundance is a high order value of these abundances that correspond in a dynamical framework to the average population and the short and long time limit of this correlation function. So as you can see, the agreement between the theory in orange and the numerics with the error bar in blue is remarkable up to this dashed orange line. So what is this line? This corresponds to the critical temperature for the equilibrium phase, where ergodicity breaking effects start to appear and the dynamics is no longer diffusive. So this concludes the first part of my talk, but since up to now I just mentioned the Lofka-Volterra model with, which is somehow a purely competitive model, I want us also to enter into more detail and to explain how we can model cooperative interaction. And so this is an ongoing work that is hopefully submitted in the next few weeks. So essentially, we start from the same, one strategy is to start from the same dynamical equation that I showed at the very beginning, but we modify this one species potential essentially by modifying the logistic growth function by multiplying this logistic function by ni minus m. M is called the Ingergo threshold and correspond to the minimal population size required to the population to survive. So given this choice of the potential, so essentially by introducing a cubic potential, a cubic dependence of the species abundances, we can model the so-called Dalí effect that describe a positive correlation between population density and per capita growth rate, which is also a proxy for the individual fitness. So this Dalí effect was first proposed by Dalí in the 30s, who was a smart observer of animal collective behaviors, and essentially observed that in many species undercrowding and not only competition can contribute to limiting the population growth. But on the other hand, aggregation and cooperative effect can have a positive outcome, a positive effect on many species that otherwise will tend to the extinction. So this Dalí effect can essentially take place in two different ways, according on whether there exists or not a positive threshold, so a so-called Dalí threshold, so a threshold below which the population goes extinct. And so in red, we have a strong Dalí effect that corresponds to a positive value of m. And in orange, we have a weak Dalí effect that corresponds to the fact that the per capita growth rate is essentially positive at zero density. And so it essentially corresponds to the absence of an Dalí threshold. So why is so important? Because essentially, even though this cooperative effect seems to be more obvious, more natural in social vertebrates, there have been a lot of empirical evidence also in insect and aquatic population. But more recently, it has been shown that a strong Dalí effect, so a population decline at small density, can also lead to surprisingly rich dynamics in basic epidemiological model. And so for surprisingly rich dynamics, I mean the appearance of multiple steady states at sustained oscillation and also catastrophic collapses of endemic equilibria. So our goal is essentially to provide a theoretical framework and well-established theoretical framework for explaining and integrate all this plethora of empirical results. And so today I want essentially to point out two main results. The first one about the phase diagram of this model for the Dalí effect, both for the strong Dalí effect and the weak Dalí effect in presence of a demographic noise and a small immigration parameter. And so to understand the nature, the fate of the emerging transition with the LD effect, we essentially perform a perturbative expansion close to this critical line in blue and orange, respectively. And in this particular case, at variance with the Lofka-Volterra model that I explained before, we found no evidence of a Gardner-like phase. So this means essentially that we have just a continuous transition from a single equilibrium phase to a phase where the replica symmetry is broken infinitely many times. And then the second result that I want to point out is the study of the species abundancy distribution at zero temperature by using a stability argument. So what does it mean? So essentially, we look at the harmonic fluctuation of the effective potential, the harmonic fluctuation that are also minimal. And in this way, they provide a criterion for marginal stability in this kind of models. So we look in particular at this condition, and the only assumption that we make is essentially to consider this probability distribution evaluated as a function of this effective potential that should scale as the absolute value of this effective potential to an exponent alpha strictly positive. And so we get a power law behavior for this distribution with an exponent alpha that has to be necessarily greater or equal than 1. So to conclude, today I present two main models. So essentially the Lofka-Volterra model as a function of demographic noise and heterogeneity parameter. And so what we highlight in this Lofka-Volterra model is that there exist two different intermediate phases where a multiple equilibrium regime emerge. And in particular, the very, very low demographic noise, we highlight the emergence of an amorphous Gardner phase in analogy with jamming of amorphous material. So I didn't have time to touch up on another problem, but I want to say that this Lofka-Volterra model without demographic noise and without immigration can also generalize to model the so-called replicator dynamics, and so can be of interest for random replicant models that turn out to be particularly timely in evolutionary game theory. And then in the second part, I present an extension of this first model to take into account cooperation in large ecosystem and essentially to describe weak and strong LE effect from which we notice the emergence of different transition, so transition belonging to different universality class, and also the appearance of a pseudo-gap distribution as a function of the effective potential. So for the future, we will be very interested in introducing a notion of space that can result in pattern formation and directed percolation phenomena, but also to understand the part of the phase diagram with a stronger interaction that can give rise to periodic cycles or stable equilibria, and then to analyze the volume distribution of the different attractors that can emerge. And so now I want to thank you for your attention. Am I ready for question?
Thank you, Ada. Unfortunately, we only have like literally 1 minute for questions, but there are a few in the chat. Let's see. So there's a question whether your definition of free energy corresponds to a Lyapunov function of the system dynamics. And I think that was in the part about when you introduced the random Lofka-Volterra part. And what did you assume about the symmetry correlation between alpha ij and alpha ji?
Okay, so as I said, so essentially this model was studied. So in the first part, I presented the Lofka-Volterra model with symmetric interaction. So I assume that alpha ij is equal to alpha ji. And so in this particular case, as I said, we can have a direct mapping within the Langevin equation, the dynamics equation that I showed at the very beginning, and the static thermodynamic formalism. Otherwise, it will be unfeasible. So the only condition that we can have is to consider symmetric interaction. And so in this case, we can write a Lyapunov function that corresponds to minus the Hamiltonian. So the Lyapunov function is essentially this Hamiltonian with a negative sign.
Okay, and
so the free energy is essentially the exponential of this. So it's essentially the log of this quantity, the exponential of this action.
Okay, hopefully that addressed that question. Otherwise, I can always discuss later and gather. And a final question from Samir. in order to model cooperation, wouldn't it be possible to add structure in the random matrix alpha ij, for example, adding conditions that for some pairs of species, both like alpha ij is negative, while for other pairs, they're both positive?
Yeah, I perfectly agree. So this was one possible strategies. So what we want to do is essentially to modify. So okay, so I want to say two more things. So one possible strategy is to take this dynamical equation and essentially modify the potential. And so with this choice of the potential, which is a cubic potential, we can describe multi-stability, and particular B-stability in this model that turned out to be particularly interesting in microbial community, because we know that mutualistic interaction can be a result, can be a consequence of metabolic cross-feeding. So we want specifically to model this Ali effect with two stable fixed points that emerge at variance with the Lofka-Volterra model. But I perfectly agree that another possibility to model cooperative interaction is to add a notion of space, and so to study, for instance, pattern formation. So also with both study the model on the so there are two possibilities essentially that I would like to perform in the future. So to reproduce the model, let's say on a lattice, and so varying this alpha ij. So taking this alpha ij just varying on a specific range, let's say in a patch. And another possibility is to add the diffusion term that is particularly interesting also for active matter and cooperative patterns in general, because with diffusion or without diffusion, you can observe very, very different behaviors.
Okay, thank you. Well, at this point, let's thank Ada and move to the last speaker of our